Yeah, welcome everybody to today's Quasiworld seminar. So our first speaker today is Sergiy Merenkov, and he will tell us about quasi-regular maps of Carpet-Julia sets. So please, Sergiy.
Thank you very much. Well, now I lost where I'm supposed to turn off my video, but I guess it's okay. You just see part of my head somehow, or my ceiling. It's a pleasure to be back. Thank you to Misha, Mario, Anina, and Sylvester. Okay, I have not given Zoom talks in a while, and now I'm struggling with all this technology. Okay, got it. In fact, the last time I gave a talk here was in the early days of the pandemic. It was the first and last time I spoke at Quasiworld. It's a pleasure to be back. I will talk about quasi-regular maps of Carpet-Julia sets, and this is joint work with Letian Shen, who is last year undergraduate at the University of Science and Technology in China, and he's applying for graduate schools in particular in the US. I'm just saying. Okay, so I will discuss Julia sets of, rational maps. So you have a rational map. As usual, we assume that degree is at least 2. I don't think I see like questions from in the chat, but maybe
Yeah,
organizers.
I'll let you know, Sergiy.
Thank you. So of degree 2, and I'll denote by J of F. It's Julia set. I'm not going to define Julia set, but hopefully most people are familiar. I will also assume in pretty much all of this talk, my rational map will be postcritically finite. Postcritically finite, which I will abbreviate as PCF. It just means that critical points have finite orbits, and almost the whole talk will be about Sierpinski carpet Julia sets. So Julia sets can have different topological types, but in my talk, they will be Sierpinski carpets. So topologically, they are Sierpinski carpets. Carpet, which is this familiar fractal. It's homeomorphic to this. Okay, one example of such a map, and that might be just the only example I remember on top of my head, is this f of z equals z squared minus 1 over 16 z squared. It's critical. It has 4 critical points. And they are 1/2 e to the I k I over 4. K is odd, 1, 3, 5, 7. So I'm just going to draw them. They're all on this circle radius 1/2 here. They are mapped to so 2 values, 1/2 and negative 1/2. Like so, this one and this one go here, and this one and this one go here. And both of these are mapped to the origin. The origin is mapped to infinity, and infinity stays. So that's the situation. The picture, I don't think I'll do a good job, but there is a central component. There is a base at infinity. There are these components that contain critical points, and there are a bunch of other components. eventually all of them. There is some symmetry to this, which my picture doesn't show. Maybe I should make it a little bit more symmetric because there is rotational symmetry. So this is Julia set of F. It's a carpet. And these are called for two components. Okay. So these are types of Julia sets we will consider. There are, in fact, whole families, infinite families of postcritically finite rational maps which have carpet Julia sets. So it's far from unique. Now I will be discussing quasi-regular maps, which I don't think, again, this needs to be defined at this seminar, so I'll usually denote it by Xi, quasi-regular map, quasi-regular map. Mostly they will be quasi-regular maps of the whole sphere, but more generally in the domains of the sphere. So they have some degree of regularity locally in the Sobolev space W12. And then, of course, there is this inequality. D stands for differential. Okay. This is almost everywhere. Needs to be satisfied. So these are continuous, open, discrete branch covering maps, really, of the sphere. When Xi is assumed to be so quasi-regular maps, of course, don't have to be homeomorphisms, but if it is assumed to be a homeomorphism in addition, then it's a quasi-conformal map. Quasi-conformal. Okay. Quasi-regular maps are locally quasi-conformal. So if quasi-regular, I'll abbreviate quasi-conformal as QC. I'll abbreviate quasi-regular as QR. And today I saw QR. Okay. So, oops. Yeah, if you have QR, then it is locally. So it's QC, locally QC away from critical points. Okay. So now let's suppose we have two rational maps, PCF, and they have carpet Julia sets. I will often will skip the word Sierpinski, just say carpet Julia sets. What we do, we would like to understand quasi-regular maps, global quasi-regular maps of C hat Riemann sphere such that C inverse of J of G equals J of F. So this is J of F. Carpet. Here's another carpet. J of G. And we're looking at quasi-regular maps of the sphere, which do this. It's in particular, this implies that J of G equals C of J of F, but it's a bit stronger. So I just want carpet go to carpet, basically, and also pre-image of carpet is carpet. Quasi-regular, okay? C is quasi-regular. This is our setup. This is what we would like to understand. Now, there is some past work related to this, and I'll state it as a theorem due to Mario Misha Lyubich, and myself. This was published in 2016. We had a similar setup of G PCF maps, PCF, carpet Julia sets. And but we looked at quasi-conformal maps, so not quasi-regular, quasi-conformal maps such that Julia set is mapped to Julia's F. F is mapped to Julia set of G. Here, you don't need to take a GX inverse of JG because it's a homeomorphism. And the conclusion of that result is that Xi restricted to the Julia set of F is a Möbius transformation. So it's a restriction of a Möbius transformation. I will mention a couple of corollaries. One corollary is that then if F equals G, then quasi-symmetry group of quasi-symmetry, again, I'm not defining quasi-symmetry, but you can think of it as a just restriction of global quasi-conformal map to the Julia set. Quasi-symmetry group is the same as Möbius group. This is what we proved. And in particular, this is finite. Finite and finiteness is an older result by Gennady Levin. Gennady Levin from the 1990s. A corollary to this corollary is that if you have a PCF map, whose Julia set is a carpet, then the Julia set cannot be quasi-symmetric to any limit set of a Kleinian group. So Kleinian group. In fact, this was one of our main motivations for this result at the time. We were mostly interested in sort of distinguishing various geometric or dynamical carpets up to quasi-symmetry. And quasi-symmetry group is, of course, an invariant. So we were interested in just quasi-conformal maps at the time. Okay, so this is all the result. Just going back to this example that I already mentioned. This example z squared minus 1 over 16 z squared. It does have some.
Sorry.
I'm sorry?
Sorry, why is it not a Kleinian group limit set?
Limit set, because, okay, so because, yeah, let me go back real quick. Because limit set of a Kleinian group always supports infinitely many, so the QS is always, how to get rid of this? Quasi-symmetry group of this guy is always infinite because it supports action of itself. The limit set supports action of the group itself, which is infinite, because the only chance to be quasi-symmetric is lambda of gamma would also have to be, first of all, Sierpinski carpet. In that case, group is infinite, and quasi-symmetry would be, so quasi-symmetry group would be invariant. So this one has finite group, quasi-symmetry group, J of F, and this has infinite.
Thank you.
Okay.
Mm-hmm.
Okay.
So Sergey, there is a question in the chat.
Oh, yes.
So the question is, in the theorem, I guess the first theorem that you mentioned, does the QR map extend to the entire plane as Möbius transformation as well?
In this theorem here?
Yeah, I'm not sure. Manisha, can you maybe?
Does it extend to entire plane as a Möbius transformation?
Yes. So basically, I am not sure if I understand this theorem correctly. So you have a QC map from one Julia set to another, and you're saying that that map restricted to the Julia set of F is Mobius transformation. Do we know anything more about the entire map that we have there? Is it itself a Mobius transformation, or can it be of polynomial type, or can it be like, are there any other properties of quasi-conformal map there?
So a priori, the QC map, it could do different things in the Fatou components. It doesn't have to be Möbius there at all. But when you restrict it to the Julia set, it is itself a restriction of a Möbius transformation. And therefore, a restriction to the Julia set has an extension, global extension to a Möbius transformation.
Awesome. Okay, thank you so much.
So that's, yeah. But a priori, it doesn't have to be Möbius in the Fatou components, of course. We don't assume that. Okay, so let's go back. Yeah, this set, anyways, we know, for example, it does have some Möbius symmetries. For example, there is a rotation by pi over 4 angle, which is also a Möbius transformation that preserves this Julia set of this map. There is also a iota. I don't know. It's z goes to 1 over 4z, another Möbius map that preserves the Julia set. That's quite easy. In fact, as far as I know, I mean, it's a bit embarrassing to admit, but as far as I know, we don't know whether this is that these two guys generate the full group. So of Möbius transformations preserving the Julia set of this map. And in general, I don't know how to get a handle. Like if you give me a postcritically finite map, I don't know how to like find all the elements in the group. There are some works which I will not go into, but I think it's I don't know. It's an interesting question too. Also, like figuring out whether this is kind of a computable question and things like that. I think it's interesting. Okay, so now I'm about to state the main result of today's talk. As I said, this is our work, joint work. So myself and Letian Shen. We posted it on archive just recently. So it has two parts. Well, it's actually two separate theorems, but I'll state them as one, perhaps. Suppose you're in the same situation, PCF maps the Julia sets of carpets. And C is quasi-regular map of the whole Riemann sphere with this assumption that I already stated. The conclusion is that if you restrict C to Julia set, then it's a restriction of a rational map, which it's a restriction of C hat. We'll call it C hat, a rational map. Rational. This is the first result. I mean, there's also a certain functional equation that is satisfied like this. This is all compositions. GM C Fn, and this is I'll come back to this equation. So for some nm prime. Naturally, these are compositions, so these powers are compositions. Maps. This is first part. So very similar, right, to the previous theorem. And the difference is that now we're dealing with quasi-regular maps, and the conclusion, it would have to be restriction of rational. Restriction of rational. And again, in the photo components, it doesn't have to be rational a priori, but you can adjust it to make it rational. The second part is when f equals g. So moreover, when f equals g, and we also assume degree of C of this a priori quasi-regular map is at least 1. Then we have the following functional equation for the extension, rational extension, f of 2k. So there exists k and L natural, which is a better equation than the one before because it only has c on one side, not on both sides as before. In particular, the Julia set of xi hat is exactly the same as the Julia set of f. Xi hat is also postcritically finite. And they share the measure of maximal entropy. Share that same measure of maximal entropy. Okay, so this is the main result that I will discuss. Before I proceed to giving some details of the proof, I would like to kind of point out some things here. So in particular to this about this equation star. Okay, so I mean, we would like to know, and actually don't know, whether it's a question whether we can somehow take this fk to the other side. Yeah, so like this question: is it true that CL equals M fk, where M is a Möbius transformation? We don't know. We don't know.
So why do you need the M there? I mean, you could just speculate. Maybe some iterates are the same, right? So
we could speculate, but I mean, in general. So very good question, Mario. So there are a couple of papers by Levin and Sierpinski from the 90s. I will talk about them later. And also a much more recent paper by Hexier, which I will also mention later. So when the question is, when do two rational maps share measure maximal entropy? And in general, the answer is this: you have to have some kind of post-composition with a Möbius transformation. But yeah, I mean, if you could do it even better, right? If just kind of more specific question, can you do it with just identity? Okay. And we don't know. We don't know. We suspect that, I suspect, maybe I shouldn't say we, I suspect that this is possible with some Möbius transformation, perhaps, here. Now, you see from this equation from star, we can sort of solve it, right? We can write it like this: f minus k f2k. But this is somehow this is a multivalued function, right? So the equation, if just f minus, or you can also write it like this if you want: f minus k fk, fk. Same thing. This is multivalued. The left-hand side is a rational map, so it's single-valued, so rational. So that just means that, you know, something, this multi-valuedness gets canceled by precomposing with some iterative of k. So this is kind of an issue here. maybe let me say a few more words about this multivariate function. First of all, even if you take this example, going back to this example, the one that I know quite well, you see, if you look at all iterates of like this, if you look at just this example and take maybe k equals 2 or something like this, yeah? So like even this, minus 2, f2, this is, okay, f is a degree 4, map, so f2 is what is degree 16. Now this here is a multivariate function, which, a priori, so like if you take a generic point, it will have 16, I guess, values or something. Maybe some of them will cancel, but it will have a bunch of values. And okay, so if you take k larger, you will have more values of this function, of course, but the Möbius group is finite. So at some point, you definitely do know that this is multi-valued function. That doesn't have to be Möbius transformation. So things like that don't have to be Möbius transformations. It's quite clear even by looking at the simple examples. But when you precompose it with something like this, then it becomes a rational map. So this is a bit weird, and it confused me for a while. And in fact, if you look at, and this is now I'm discussing in more detail the work of Hengxi, from 2015. He exactly looked at when two rational functions share a measure of maximal entropy. And he deduced this equation. Actually, he deduced it from earlier work of Levin and Shetitsky, and Levin by himself. So an equation like this. It was exactly after, kind of trying to put this fk to the other side. And what he realized, and he has a paper in Advances at that time, that, well, one needs to, it's pretty straightforward, one needs to look at this kind of algebraic variety in C hat 2, fk of x equals fk of y. You have to look at these things. It sits in C hat 2, C hat cross C hat. If you have such an equation, then you have an embedding. Well, actually, it's not an embedding. It may have some singularities of that sort, fk gl. It takes C hat and embeds it into, well, not quite embeds, to gf. This equation gives us, and okay, like I said, there are some singularities, but there is a certain normalization procedure which resolves the singularities, and you can speak of the genus, and the genus will be, of course, genus 0, because, well, you put C hat in there, so it will have genus 0. The problem is this variety doesn't necessarily have a by degree 1. So by degree is the degree of a projection of this variety to C hat. So you have two different projections onto the first component and onto the second component. So he shows that the both degrees are the same, but even in genus 0, they don't have to be 1. So this GF, it splits into some irreducible components. And of course, there's one trivial component, which is the diagonal. And this has by degree 1, genus 0, everything is okay. But then there are some other components, and they may not have by degree 1. So by degree 1 would roughly correspond to a Möbius transformation. That it would mean that you can actually put this 1 to the right, and there's a Möbius transformation there. Anyway, so I don't really want to go too deeply into this algebraic geometry things, but I do recommend this paper. Whoever is interested, it's Hengxi, and I think the title is something like when do two rational functions share the same measure of maximal entropy. Okay. Maybe I'll state one more. The main result of Hexier also. Hexier 2015. So if you have FG, non-exceptional. Non-exceptional means so these rational maps don't have to be postcritically finite. They don't have to have Carpet-Julia sets. Non-exceptional means that they are not power maps. They're not latte maps. They're not Chebyshev polynomials. So just usual exceptions. Then the following are equivalent. They have same measure of maximal entropy, same measure of maximal entropy, and there exists capital F and capital G. These are iterates, respective iterates. Sorry about my handwriting. Such that Fg equals F2 and Gf equals G2. So this is kind of the equation that I just mentioned. If this is iterative Xi hat, Cl, this is an iterative Fk, this is F2k. Also, he gave examples. Of rational functions Fg. They have same measure of maximal entropy.
Sorry, Sergey, in your
Yes.
theorem, do you also have the other equation?
Which other equation?
So like, I mean, right now in this theorem that you are writing, right? So you say that you have two equations for the composition
yeah.
of F is G and the other one.
Yeah, we do, but we don't really care about this one because we would like to solve things for Xi. We'd like to have Xi hat on one side only. But yes, we do.
Okay.
It just follows from yes theorem. Yes, that's correct. So he gave examples of rational functions which have the same measure of maximal entropy, but so no iterate of F equal M composed with iterate of G, where M is Möbius transformation. So they don't share. So like they don't. Iterative F is not equal to iterative G, no iterative G, and not only that, but you cannot even, if you post-compose with Möbius transformation, it doesn't help either. And by the way,
examples PCF are the examples.
They I don't think so. No, now I don't remember, but I don't think so. And yeah, this is also a good question because for PCF it could be still true, or maybe for PCF with Carpet-Julia sets it could still be true. So there are lots of things that to explore. But I mean, these examples are not quite trivial. And by the way, for polynomials, this is again result from the 90s, I think, that two polynomials share the same Julia set if and only share the measure of maximal entropy if and only if an iterate of one of them is equal to another iterate of the other one post-composed with a Möbius transformation. So for polynomials, this is true. For rational maps, this is not true. Okay, and what was known since 90s, this work of Levin and Chetitsky, is that Levin. Okay, so this one is difficult. I think like this, 90s. Is that the measure, this is a measure of maximal entropy, are the same if and only if F inverse F Fm equals G inverse Gn. So again, f and g are themselves iterates of little f and little g. And then maybe you have to take some other iterates of them as well. So they had this kind of equation. And Ye derived his theorem, the one that I stated on the previous page, from result by Levin and Sierpinski. It's actually quite elementary to derive it, but I like it better because you only have somehow Xi, like our unknown Xi, is only on one side, not on both sides, as in Levin Sierpinski's work. Even though, like I said, it follows from this. It's quite an elementary, like a pigeonhole type principal argument to deduce this Hex's result from this result. Okay, so I'm getting short on time. I should probably move to a little bit closer to the outline, the proof outline for our result with Letian. Proof outline. A lot of it follows the same steps, as you can probably imagine, the same steps as our paper with Mario and Misha Lyubich. And the only difference is that some of the arguments needed to be localized, so somehow somewhat adjusted. But the new ingredient, I think, is boils down to this kind of considerations of measure maximal entropy. That again, at the time we were aware, we knew this result, but to me, when I looked at it, it wasn't very illuminating, like how, you have some multi-valued functions on both sides, and what do you do with it? But Hexy actually distilled it quite nicely and constructed examples, and it was actually published at about the same time our paper appeared. I was not aware of his results at the time, and I don't know whether Mario or Misha were. So I'm going to do proof outline. I'm going to simplify things, just assume G equals F, though most of it doesn't need this assumption. The first step is when you have Julia set of a postcritically finite rational map. This is where it all starts. If you know it's a carpet, it's actually a nice geometric carpet. Its peripheral circles are uniform quasi-circles. They're uniformly relatively separated. By result of Mario, you can quasi-conformally uniformize it by circle carpet, round carpet. Round carpet, which we also sometimes call Schottky set. In honor of Mario, I denote this map by beta. Okay. Now, I extended some of this. We had some early results with Bruce Kleiner about rigidity of Schottky sets. I extended some of them to so-called relative Schottky sets in about 2014, 2012, 2014. There are a couple of different papers, 2014. About relative Schottky set. So relative Schottky set, it may have some, maybe just one non-round component, but everybody else is round inside it. And so we call it relative Schottky set, relative. And suppose I have another relative Schottky set. So it's S tilde, and I have, say, homeomorphism between them, or a local homeomorphism. Actually, it doesn't really matter. Anyways, we call it Schottky set. F is a Schottky set, Schottky map, sorry, Schottky map. If for every P in S, limit of the difference quotient, just like in calculus, but we send Q to P, but we restrict Q to S. Okay, so this is not like in calculus. Equals f prime of P, so it exists, not equal to 0. And in addition, we require that f prime, so defined as continuous in S. So we call, once again, we call a map between two relative Schottky sets. A Schottky map, if for every P here, this limit of the difference quotient along the set exists, not equal to 0, and in addition, this so-defined map is continuous. Okay. Now I proved that this was 2012, was first paper. I proved that if you have a quasi-conformal or even locally quasi-conformal map, whatever that means. So quasi-conformality constant can RLS. So these are relative Schottky sets, locally quasi-conformal. Means that when you get close to the boundary of this domain, then the constant may get worse, essentially. And if we assume that the S has measure 0, okay, so locally quasi-conformal, S has measure 0, then F is a Schottky map. So derivative does exist. It's continuous. In fact, I proved that the derivative is a Lipschitz map, locally Lipschitz map. There are some recent results by Yushen Lu and Yonchun Zhang. They studied some circle packings associated to finite subdivision rules, and they have some regularity results similar. They proved that a certain derivative also exists and is Hölder. So in my case, derivative is locally Lipschitz stronger. In fact, I conjectured in this paper that maybe it's actually C infinity map. So like if you take derivative over and over, it will always exist, just like conformal maps. As a corollary of this result, if you happen to have a quasi-regular map, then it restricted to S minus critical points is a Schottky map. So once we use Murray's result and uniformize things by round carpets, we're dealing with the Schottky maps, which are quite kind of like conformal maps between these relative Schottky sets. Somehow, this is what you should think of. And they, just like conformal maps, they enjoy a lot of rigidity and even more than conformal maps do. For example, if you happen to have, say, a relative Schottky set, you take a point here inside the set P in S, and suppose you have S, I don't know, you restrict to some domain U. Suppose S intersect U is connected, and let's say that at F you have a Schottky map that takes S intersect U to S, Schottky, such that f of p equals p, it fixes point p, and also a derivative defined on the previous slide is 1, then f is identity in S intersect U. So it has more rigidity than conformal maps do. Yeah, so you can certainly have conformal maps, locally defined conformal maps with these properties that are not identity, but for Schottky, they would be identity. It's a simple proof, but I don't have time to outline it. A little corollary of this rigidity, maybe I'll state it as a proposition. Proposition is the following. So if you have a sequence of maps as U to some other UK, so these are Schottky, say they are Schottky homeomorphisms, locally defined. We will assume that this is locally porous, basically locally porous means that locally peripheral circles appear on all locations and scales. Suppose Fk converges to F like this, locally uniformly. And then there is a minor assumption that's always satisfied for when you're dealing with dynamical objects like postcritically, like Julia sets of postcritically finite maps. I don't even want to bother stating it. Minor assumption, always satisfied in our context. Then conclusion is that they stabilize. This sequence stabilizes. So starting from some number, they're all the same map. So like Fk equals FL, Fm, L for KL larger than some number. So they're all the same map in S intersect U. So yeah, the Schottky maps, they have quite a bit of rigidity, and more than, again, if you're thinking of like sequences of conformal maps, you wouldn't have such strong conclusions, but for Schottky, you do. Okay, I have about 4 minutes. Just a brief outline of why it works, like why it helps us. So suppose I have this quasi-regular map, J of F, J of G, quasi-regular. Now I'm assuming it's Schottky because I kind of translated everything. I conjugated everything to this Mario situation when the set's around. Then there is I'm going to choose a point P, which is the periodic point of F, periodic. In fact, I'm going to assume it's fixed because I can always pass to iterates. And then this is what I will do. I'll take some domain U. I don't know, I assume U intersected this Julia set is connected. I'm going to assume that F is actually fixed. P is a fixed point of F. There's a round carpet going on here. I'm going to take F minus N here, which will take this larger neighborhood into smaller. So F minus N for the whole sequence N, and then I will compose it with Xi, and then I will blow it up by some iterate of. So this will be a small guy, and then I will compose it by F to the power, well, let's assume G. I said that they're the same, but I'll do G here, Gm. So M depends on N. So I have a whole sequence, F minus N, Xi, Fm, depending on N.
G.
G, thank you, G, depending on N. So these are Schottky maps. A sequence. I picked them so that the diameter of the image is approximately 1. This technique is called conformal elevator in dynamics. So this is a sequence of Schottky sets. I can choose a subsequence that converges locally uniformly. And then, and then I use the stabilization result that I mentioned, and so we will have G minus M, I don't know, M prime, G, okay, not minus, MK here, Xi F minus NK equals G N ML Xi F minus NL for some K less than L, both are large. And okay, so then we can actually cancel here this precomposition. If we were careful enough to start with, we could start with some kind of consistent sequence of preimages, and this implies this equation. Cfn equals gm prime c. So this equation that I stated on only on S intersected U. But look, I mean, both sides are Schottky maps away from critical points. So, and there's this uniqueness result, so we can kind of analytically extend them to the whole Julia sets. And so we have global. So actually this implies global. So you have a global equation like this. I'm out of time. Just a few comments. So to the other result when you can somehow only, so to this one, I didn't get to this one. And okay, so this functional equation, just proceeding very similarly to what we did in the paper with Misha and Mario, you can redefine the map C in the Fatou components, first in periodic Fatou components, then in all other Fatou components, so that it becomes rational map just by using this functional equation. So this is number one. Number two, you can manipulate this a little bit. I mean, you can certainly, so if f equals g, this equation can be reduced to equation like this, f 2k c L equals on the Julia set equals, what did they say? Fk CL. No, there's no L. There's no L. Never mind. Fk like this. You can do this. You can always post-compose by some iterator of f. And what this tells you is that fkc commutes with fk, which means that fk, c, and fk have the same measure of maximal entropy, and this measure of maximal entropy is mu f. If two maps commute, two rational maps commute, they have the same measure of maximal entropy, and this has to be mu sub f. And then just once you have this result, you know that C would also have to have the same measure of maximal entropy of mu f, and that Hex's result implies the identity that we wanted, which is, what does it say? Fkxcl equals F2k. Okay, I got to stop here because there's another speaker after me. So thank you for your time.
Yeah, okay. Yeah, let's thank Sergiy.
Cool.
And let me open the discussion. So comments or questions. Manisha, you had a question.
Yeah, so in the theorem about stability of the sequence of our maps, so I have two questions actually. So Fk, when you're defining Fk to be S intersect with U and the image is UK, do we have some relation? Eventually, what I understand is UK should also stabilize into some, right?
Well, yes.
And
Correct.
then a priori, so when we say that it stabilizes for all k greater than or equal to n, this might be a naive question. I was wondering, like, what does n depend on? Like, how are we retrieving n? For different functions, I suppose that there will be different n's, but what is the function then?
There is no quantitative control. It's just pure, it's just proved by contradictions. Suppose things don't stabilize, then you have a contradiction. No quantitative.
I see. Okay. Thank you.
Mm-hmm.
Well, let me ask you a question. So if I understand you right, I mean, in the case where you just look at quasi-regular self-maps of JF, right?
Mm-hmm.
So you're saying, okay, you get this equation. I mean, the first equation here on your page, essentially, right, for G equal F. And then you're saying you can improve this equation by looking at the measure of maximal entropy, right? I mean,
yes, correct.
So this is a new ingredient, right? That
this is a new ingredient, yes.
I see.
Yes, this is exactly. This is something that, I mean, we saw this equation. I saw this equation by Sierpinski and Levin. that have on both sides, they have F inverse F and G inverse G. I didn't know how to make use of it. Number one. So that's kind of one thing why we didn't look into that. And I think, I mean, another thing is we were mostly concerned with groups rather than just some rational dynamic or quasi-regular maps. So could we have done it, I don't know, 10 years ago? Probably some things, maybe not all of it. I think Hexie's paper kind of crystallized a lot of things.
So Hexie is a former student of Laura De Marco, right?
I think so. Yeah, they have a joint
Yeah, I
paper
mean, I was
together.
somehow aware that he's working on something along these lines, but at the time I was
Mhm.
certainly not aware of the specific results.
Mhm.
Let me ask you another question. I mean, so didn't you prove something about the case of, you know, when you have a limit set in quasi-regular maps, self-quasi-regular maps of limit
Yes,
sets?
yes.
And what about just the standard square carpets? Do we have any results on
No,
that?
but we have some corollaries. Yeah. So we even in our paper, a couple of papers, we have corollaries that. So for standard carpet, we don't have any locally quasi-regular self maps of standard carpet. We have this.
Mhm.
And we also have, I mean, I also have this for limit sets of Kleinian groups. This is another thing that I wanted to mention. So carpet's somehow very special in this respect. And if you have a basilica Julia set, or you have a gasket Julia set, all of it, whatever I said, you know, doesn't work, doesn't apply. You can easily construct quasi-regular self maps of gasket or basilica Julia sets that have nothing to do really with dynamics at all. And there are lots of results, like recent results by Yusheng Lu with some collaborators, in particular this one with Mahanji and Sabia Mukherjee. They actually proved that they constructed an example of a fat basilica that is quasi-symmetric to a limit set of a group. So like for basilicas, for gaskets, things are quite different, much more flexible.